The comparison test of convergence. Let's consider two infinite series with non-negative term infinity sigma, n equals 1x n and infinity sigma n equals 1y n if x n less than or equal to y n for sufficiently large values of n, then if infinity sigma n equals 1y n converges, then infinity sigma n equals 1x n converges too, and if infinity sigma n equals 1x n diverges, then infinity sigma n equals 1y n diverges too. The rule is not only true for geometric series but for all infinite series. However, for now we will illustrate this convergence test with infinite geometric series only, as we have not explained yet the other infinite series. For example, if we consider the infinite geometric series, we have the following shown on screen. It is easy to see that this is a converging series, as the first terms, we have the following shown on screen. And so on. Therefore, it is easy to see that this series is identical to that discussed in the first example in theory, the one with the figure, the sum of which was equal to 1. Therefore, the other infinite geometric series, we have the following shown on screen. Is also convergent, we have the following shown on screen. For any positive integer, n. Indeed, we have the following shown on screen. Thus, we have x1 is equal to 1 over 3 and r equals 1 over 3 too. Hence, from the formula for the calculation of the sum of an infinite geometric series, we have the following shown on screen. Let's consider now two diverging geometric series, we have the following shown on screen. Where the general term of S1 is x, n equals 4 2, n and that of S2 is y, n equals 5 3, n. The first series is diverging, as the more the value of n increases, the more S1 increases too. Therefore, this is a diverging geometric series, as when n points to infinity, so does S1 as well. Obviously, when comparing the general terms, we obtain the following shown on screen. For all positive integers n. Hence, if we prove that S1 is divergent, it is not necessary to prove that S2 is divergent. Let's check the convergence of S1. In simple words, a series is convergent when the difference between two consecutive terms decreases by the increase of n, as the terms' values tend to increase less and less until they converge at a fixed value. The sum of the first terms of S1 we obtain the following shown on screen. It is obvious that the difference between two consecutive terms increases more and more, we have the following shown on screen. And so on. Therefore, S1, x is divergent. Based on the rule, so must be S2, x as well. Indeed, we have the following shown on screen. It is obvious that the difference between two consecutive terms increases more and more, we have the following shown on screen. And so on. Therefore, S2 is divergent. Example. Check whether the following series are convergent or divergent by comparing them with a known series. We have the following shown on screen. Solution. A. We have the following shown on screen. We can check the convergence of the known geometric series, we have the following shown on screen. To see whether S1 is converging or not, we have the following shown on screen. Thus, x1 equals 3 over 4 and r equals 3 over 4. Therefore, since S is an infinite series, we have the following shown on screen. Given that this series is convergent, S1 is convergent to, we have the following shown on screen. Hence, it meets the first condition of the convergence rule. B, we have the following shown on screen. Let's check the convergence of the series. We have the following shown on screen. In this infinite geometric series, x1 equals 3 and r equals 3. Hence, we cannot apply the convergence formula. We have the following shown on screen. Because it is true only for series where -1 less than r less than 1. Indeed, it is evident that the terms increase more and more. We have the following shown on screen. And so on. Therefore, the series S is diverging. This means that since S1 equals 7 Sn, then the original series S1 is diverging too. That is all for lesson 12.4.4. To continue this tutorial, please watch 12.4.5, the special types of infinite series. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.